Okay, so good afternoon. So this is the second talk of Professor Fuad Alaskerov from the National Research University Higher School of Economics in Moscow. And the title of the talk is Choice Procedures in Big Data Analysis. Thank you again, Professor Fuad, to be with us.
Thank you very much. It was really a pleasure. It is a pleasure to be here. And just a few minutes before we were in the museum, Ricardo Brennan Museum, and I decided to stay there. Boris insisted upon that you should go, you have a talk. So this is another a bit different story, which we did some years before. These are my co-authors, and this is a presentation structure. I will not go. And what is the idea? You see, the search problem in big data analysis, it is very, very urgent problem in a sense, you see, and we confront this problem some years ago when I did the work for some German firm. This German firm, they found British firm found me, and I did this work in which there were one of the problems was to analyze customers' behavior of this customers of this very retail network in one of the European countries. I cannot say which country is because of NDA. And they gave me data covered more than a year, 1.4 million people, and 400,000 goods. So, and they gave me this data absolutely in terms of everyday purchases for more than a year. This was the first time when I confront this big data problem. And so the emergence of problem it is long ago, you see, and how usually you work with this very data. We have this evaluation of documents by some assessors, yes. We derive some features. Learning system return us some kind of evaluation function. And then when we have a new document, then we apply this evaluation function and classify it where to go. So, but when we apply these classic models of search, especially support vector machine, etc., it turned out that in the whole bunch of data, it worked 4 hours, 15 minutes, you see, for one search. And I said that to my guys, that if we work in this very speed, we will not finish this work in 5 years, but nobody will pay us for 5 years. So, and then I started to analyze the problem. I will talk about it. And what is the problem? You see, unfortunately, I don't have here laser. We have a finite set of alternatives, okay, evaluated by n criteria, different features, okay. And so to each alternative, we have the vector of criteria values for every alternative x. And what we should do, we should transform these vectors into some kind of ranking. The first most, let's say, the first vector which fits us the most, etc. You see, that is a problem. And then I when I was young and I wrote the book with my teacher and great friend, Mark Eiserman, at that time I wrote, in fact, a chapter in the book about the superposition of choice function. The problem is that differential equations, the course on differential equations, when I was a student, I went to the lectures of Arnold. Vladimir Arnold was a great mathematician of 20th century. And with Kolmogorov, at that time when I went to his lectures, he was rather young. But in 1956, 20 years before being very young, he with Kolmogorov, Andrei Kolmogorov, they found a solution of 13th Hilbert problem about superposition. Okay, and I thought about it that we might, I understood that the problem is generally solved, but I thought about superposition of choice functions in terms of maybe to find something interesting for a very specific class of functions. And we know 5 groups of choice functions. These are scoring rules, for instance, where we look at the ranks of alternatives in this very rankings. Rules using majority relations, for instance, we have majority relation if more people or more criteria say that A is better than B. In majority relation, A is better than B. Okay, and then we apply different rules to majority. Rules using value function, for instance, evaluate how many in lower contour set have the alternative, sum up, and say that, this is the value of this alternative. Tournament matrix, it is again, you see, we consider this very evaluation of alternatives via criteria as a tournament, as a game, you see, multiple round game. And Q-Paretian rules are the rules which it was not at that time when we wrote this very book, but much later I proved, I will talk about it on Thursday on management department. I proved the social choice correspondences. I made an axiomatic analysis of social choice correspondences, and these are new type of rules which came from this social choice correspondences. In total, we have about 30 procedures. For instance, let me explain just a couple of procedures that, for instance, Borda rule is the following. You see, Li of x is lower contour set. As I said, you see, I look how many, if I consider these rankings as a ranking of to be better, yes, A is better, has upper values than B, A is better, okay, in the ranking. Then we look how many these alternatives are in the lower contour set. So for how many alternatives X is better than others, okay, in different rankings. Then we sum up this, and this gives us so-called border count. And then we sum up, we evaluate this border counts and say that this is the best one. Or Simpson. We have this matrix where we write in how many times A is better than B. Then we take a minimum of this and maximize these values. This is the Simpson rule. And what is the complexity? For instance, for border rule, complexity is n multiplied to k plus 1. K is the number of criteria. For Simpson rule is n squared multiplied k plus 1 plus n. And I remember very well that when I suggested this method, etc., my guys told me, please, only linear complexity. You see, the search will be too long. So only linear complexity. And then another rule, which was I found again. You see, in classic choice theory, classic models, they work as follows. You see, we compare alternatives, say this is better than this, so we disregard this. Then we took another alternatives, which one is better? This is worse. We keep this, disregard this, and go in such a way through all through all alternatives. This is a classic choice theory. It is used in all economics, etc., etc. But in 1956, Herbert Simon, he was a great scientist, and some years later he got a Nobel Prize. He criticized this very ideal approach, saying that people never choose based on pairwise comparisons. There is, he said, satisficing level of our choice, and everything which is above our satisfaction level is okay for us. Everything below is not good. And then I made this very model years after. It was 1989, something like that, maybe 1990s. Look over there. X belongs to the choice from X capital. X capital is our set from which we choose something. And only if, I'm sorry, it's wrong. Not Xi. U of X, utility of Xi, if we consider only one criteria, utility is above V of X, where V of X is this very satisficing level, which is defined for our set. For instance, if we go to buy yogurt or milk, for me, satisficing level, for instance, is it should be not very fat, less than, let's say, 2%. Okay? Everything below 2% is okay for me. Everything above is not good. Okay? So I do not compare them one by one, you see. Just take, more than 2%, not good. 1.5, okay, I take it. How we can define this satisficing level? There are many ways to define it. I wrote about it in some books. For instance, mean value. This is my set of alternatives, okay? We take a mean value. Everything which is above mean value, average value, is okay for me. Below is not good. In fact, we might do many other ways. For instance, take a 10% of upper level, 10%, and say everything which is above this 10% is okay for me. Everything below, not good. Or many, many other ways. Okay. And complexity of super threshold rule, I called it in that way, it is linear, yes. So we can process a huge amount of information, but in the search problem, we have one more thing. We don't have one criterion, right? So we should go through one more step. This is a classic model of choice. Again, I worked on this years ago, and it is proved that this very model and satisficing choice are equivalent. Okay, so this is and now we come to the superposition. I will keep this very presentation, so if you have questions or you would like some publications, etc., just write me or write to Francisca and I will send you. Okay, so this is the problem of superposition of real-valued functions. The story is the following. You see, I will not go too deep in this very story. The story, Hilbert stated the following problem. The polynomial of seventh power, is it possible to find the roots of this polynomial, of this very equation, using superposition of real-valued real-valued functions, okay? And Kolmogorov and Arnold showed that it is possible, and it is their work of 56. In fact, there were about 3 articles of them in this case, and in fact, it is still there are a lot of works on this very directions, and I was working on this from point of view of choice functions. In 2007, my PhD student Yetkin Chinar and I wrote an article concerning this Q-scalar method and its superposition, how it's reduced to one-stage model. And let me explain you how it works. We have n criteria, okay? We have choice functions related to this each criterion, okay? What does it mean, choice functions? What, for instance, by this super threshold rule, okay? And then what we do, unfortunately, I cannot show you this. You see, I first take some nth function, choose. What is chosen, I put it as a input for CN-1, okay? What is chosen, next, finally come to C1. You understand? So sequential choice. And you understand that this very super threshold rule is linear. So I just apply several times linear model, okay? This is the way. This is for 2 functions only. This x is my initial input to the model, okay? C1 is the first function. We choose y1, put it to the C2, and get final solution. Is it clear? If you have questions, just ask. And then we have several mechanisms, so-called. In fact, you see, we can use classic mechanism, non-classic mechanisms, and there might be the following. You see, for instance, at the second stage or at the first stage, we might choose, for instance, Pareto optimal elements, okay? Then use the next stage or whatever. And then there are axioms in classic choice theory. There are axioms showing to these choice functions to which axioms they satisfy. And we can, these are axioms. I will not go too much about this, you see, but they are very reasonable axioms. They used by, they introduced by many different people, you see, used by John Nash, by Canestero, etc. Many names I can say. And for instance, monotonicity condition. You see, if my preference for A is in new condition is better than B, as before it was not so good, but A is chosen. But now A is moved up, then A must be chosen, right? Because it improves its position. Okay. So, for instance, we can look at the examples. At the first step, we'll use Maximin procedure, then Borda, or Borda procedure, then Maximin procedure, and we can see, as in classic choice functions, as in classic model, many conditions are not do not satisfy, you see, for this superposition functions. The same here, we have more or less the same here. Okay. In this case, you see, we have this several models now in which you see information about utility of alternative is not specified, yes, and then we might put these very values and order of elimination by just manually, okay? Or it is specified about utility, yes, then we can use these very models to use it. Okay, so that is two methods which we used. Super threshold echelon based procedure. Echelon based meaning that we have some echelon and set that okay. If it is above echelon, is okay, below, not okay. Or distribution function. If I have some observations concerning this utility, I might use the distribution function and say that, okay, take 1/3 of these values, for instance, upper values, okay? So this is, for instance, how we can choose this echelon criteria. It might be max minus minimum of phi, yes. This is distribution function. You see how we can have these different distributions concerning high utility values, other alternatives, rest. For instance, if we have this evaluation by assessors, you see, high means they make usually evaluation between 0 and 5. So we can look at the distribution for 4, 5, and all others. It's from 0 to 3. Okay. Okay, and what is the application? Application was very interesting. First of all, we did it for this very data from this very country for 1.4 million people, all this data concerning their purchases. And it works, you see, I can tell you a fantastic thing, you see, if in support vector machine it worked 4 hours, 15 minutes, in this method it worked 15 minutes. Even less than 15 minutes. Okay. And we really used it very widely for this problem and solve it really very fast. Now, and after that, we apply this very model to data from Microsoft. 1,175,000 documents and 136 criteria, parameters, okay, factors. And this Microsoft, they give it to, especially, you see, they download it, everybody can taste his or her method. And we used it with support vector machine for and make a comparison. Super threshold echelon based procedure for 4 and 3 upper level, okay. Only for 4 and based on the distribution, okay. These are results, okay. SVM gives 49% of accuracy. Our method with test 2 is super threshold echelon based procedure for upper level 4 and value, 84% of accuracy. And for this very set of data. And finally, please, if you have questions, just ask. And finally, we apply this very data to tornado prediction. And it was interesting stories that I was in Greece, I think it was. I gave a plenary talk there, and after me, some colleague from the United States gave a talk, and he talked about this tornado prediction. And I told him that we have some new models. If you like, maybe we apply this very new models to tornado prediction. He said, why not? They sent us data, and these are the results. So we have parameters of mesocyclone with 83 parameters, 83 features. You have question? No? And the goal is in which case this mesocyclone is transformed to tornado. Okay? This University of Oklahoma gave us data. This first we clean data, missing data, incorrect data range. There were such data also. Correlation analysis, distribution analysis, and this is the measures of model efficiency. And we can see that this critical success index, which is used in this very field, is the true tornado prediction to false tornado prediction, no tornado forecast. Okay? Then we apply this very model to this data, and we get 61% of accuracy, which at that time when we got it, I said, guys, that we spent time for nothing. 61% is nothing. They brought me an article and said that the best results is 57%. And it was written in this article that any 0.5% of improvement of this is a great result. We get 61. And so we have this very result. And then I have another model in my mind. I asked my colleagues in America that sent us a bit more detailed data. I have some model, maybe it will work. Maybe you know that the tornado prediction is 61% is the best one today, but it's not very high, and they did not respond. But in America, for Americans, I mean, in the United States, if they don't respond, this means what? They don't like to, they cannot say yes, but they don't like to say no. I called my friend in America and said, what does this mean? He said, you will not get data, because if you get data at the morning, at the evening, FBI will come to their office and said, why you sent to Russia this very data. I was so surprised. I said, you see, we don't have tornado, and if somebody's house is burning, doesn't matter who came. The problem is he should come with water, right? He said, no, you will not get, and it's I still don't get, but I have a model. Maybe you know that America every year spent more than $1 billion to resolve the after tornado problems. There are a lot of human deaths, etc., damages, etc., more than $1 billion. But still they didn't give us. So we published some kind of articles on this. These are articles before, and we have this very results. We got patents. We got American patent for these new methods of search. We got the certificate of International Society of Intellectual Property Rights, I think, Russian patent, and we also published several articles. I'm sorry. We have also the article in Nature about this very tornado prediction. Thank you, and I will stop here.
So there is some comments or questions. Okay, I'm not very familiar with the choice theory, so I could not understand very well how you use this to the prevision for tornado, for example. What are the data?
It's not a problem of choice theory, Francisco.
Yeah.
It's an apparatus. You see, we have this 83 parameters of mesocycle. Yes.
Parameters, you mean features?
Features, yes,
Okay,
yes.
which
Criteria,
describe.
yeah.
Okay.
And the problem was to say when this mesocyclone will switch to tornado, because many of them will not switch. And then we first analyzed these 83 parameters and understood that there are only 6 parameters which can be chosen.
Yes, but how will you do that?
This is by correlation analysis,
okay.
etc., etc.
Okay, classical
method, yes. And then after that, we use this very idea of superposition. You see, so many cases switch to tornado. Okay, we choose them above some level. The results will be given to the second parameter, third parameter, etc. And then we got this result that this 61% of our forecasts were correct.
Okay, thank you. And what about the application on the documents? So you have a lot of.
We didn't publish it. In fact, you see, it was just we did it, we liked it, and forgot it. As I told you, for publication, my co-authors are responsible.
Okay. Okay. Any other question or comment?
Professor, thank you for your talk. Are your methods faster than the SVM, for example?
Yes, sure.
How much?
You see, as I told you, for this very enormous sample with 1.4 million people, with all this data, etc., SVM worked 4 hours 15 minutes. Our when we apply our method, worked 12 minutes.
Okay, thank you.
We did not, in fact, check this on really very different data, etc. We just applied it, and that's all. Francisco,
yeah. Thank you for the talk. In that model where you have multiple choices that are applied one after the other.
Sorry, once again.
So in your model have the choices applied one after the other, right?
Yes.
In a chain. Did you explore how to choose the order when you apply? Because it seems that
this is a very right question. And in fact, you see, it might be done in two ways. Way number one is by analysis of distribution functions for different criteria and looking which one will give us more accurate result to use it first, for instance. Or very often we just play this with this order.
Yeah, and maybe another question. Have you applied or thought about in the case where you don't have all the data at once, for example, because if the data is so big, you might not be able to store it all at once, or maybe it's transmitted somewhere. So like in streaming data, can you apply this?
Yes. In fact, we now we will write, the article is under preparation, this is a work in which we can do it sequentially. You see, for the part of data we apply it, then add another part, etc. Yes, and there are some ways to evaluate what is the best. Yes, it will be published, I think, maybe at the end of this year.
Okay, great. Thank you.
So, any more questions or comments? No? So, thank you very much again, Professor Fuad, for this nice presentation.